was the resonator that was under the heater. You can actually see the discoloration here because of the positive TM. Okay? And please feel free to ask any questions if you have any, okay? As I go through this.
So we're looking down on the heater, on the resonator there?
So here?
Yeah, what's the orientation of the resonator?
Yeah, you're looking down. You're looking down. And the same thing here, you're looking sort of top down. Yeah.
And the resonator, the heaters are only over part of the resonator?
So, so we have two heaters here. We're only switching on this heater here.
But that big, the square is one big resonator.
Well, this is a die. The resonator is actually just this thing right here.
Okay, so that's two resonators.
Yeah, so this is right. So if we want to do differential sensing, right, this would be how we would do this. But the heater allows us to preferentiate the positive one or the other, right? If both of them would be connected. Okay, and then finally, okay, and so this is the resonator, right? So we have the resonator here. It's a MEMS device. It's actually a very thin membrane, piezoelectric membrane. There are acoustic waves that are being sent back and forth, right? So this thing is very thin, very light, has a relatively high frequency, which means it is very sensitive to changes in mass. And for us, this is perfect, right? Because we really want to have a very low limit of detection for our device. And so in this case, it's actually so sensitive to everything around it, it has to be wire bonded directly to a driver CMOS circuit, which is essentially what forms an oscillator. And then the whole thing is that this thing basically will oscillate at the resonant frequency of the resonator, which will change if we add mass to it, right? And so if we just track that resonant frequency, then we can essentially back calculate how much mass is on the resonator. Okay? So, and then, because this is, again, very small, we really need very little flow through the